Good morning, everyone. So indeed, I'm going to talk about the thermal aspect on taps. I think relating to the acoustic part, it's important to know how things work. And I'm going to focus also on implementation of a model-based predictive controller. It's an important word. So it says that it's based on a model of the building. It's a controller that defines its action based on the model of a building and of the HVAC system. And it's also a predictive controller, so it can look into the future and say, okay, in a few hours this and this is going to happen, so I have to take action now. Okay, introduction, why taps? From the installation point of view, taps is a good thing or a good option because it's a thermal storage. Yeah? You can use it as a storage for heat and cold, which also means that you can decouple what is happening on the installation side and what is happening in the building zone. Yeah, that might be useful to avoid peaks for the installation, things like that, or to shift energy production from energy use in the building to cheaper energy tariff times. What is important in taps, if you look at it as a thermal storage, that it's actually quite difficult thermal storage. Why is that? Because what you can do is you can control the heat you put into the taps by switching the water flow on and off, or changing the water flow by changing the temperature. So you have control on that, but you don't have control on the amount of heat which is going from the taps into the zone. That's just defined by the temperature difference between the surface and the air, or the surroundings of the zone. So that makes it very difficult to use it, because if you're talking about thermal storage and you want to use it as peak shaving device, for example, you need to have both control of the amount of heat you put in and the amount of heat you can extract from the thermal storage. And in this case, you cannot do that. So that's very, very important to take in mind if you talk about taps. When designing a system with taps, you should take care that there are three important thermal characteristics. First, it doesn't have that much power. Yeah, you have to face it. The power is limited. You have to take care by making a building which doesn't require so much power. If you're installing taps in a building that requires more power than the taps can deliver, well, you just have, from the control point of view, you don't have a system that can work, because it's not able to deliver the power that's required. It has a very large thermal mass, really huge thermal mass, so it takes a very long time to heat it up and a very long time to cool it down. It's also important, certainly for control also. And which is also important from the installation point of view, it takes quite a high thermal power to heat it up. I'm going to show some examples on that because it's important to know. This is a graph that actually shows the three characteristics very good. So what is happening here, I have a slab, thermally activated slab. It's 20 degrees. The zone below and above is also 20 degrees. And I'm going to start heating that slab with water of 30 degrees. So I'm going to put a step into the water flow. And then you have here the thermal power, which is going from the water into the taps. And this is a thermal power from the taps into the zone. Yeah. So I can see here clearly, okay, it has a limited steady state thermal power. It's only like 60 watts per square meter. Okay, for heating that's okay. For cooling, it's quite limited. It takes a very long time before the zone notices something happening. So after 4 hours, you are at 60% of the steady state value. So it takes a very long time before the zone notices something. So you cannot come into the office and say, okay, I want the heating on. I turn it on, and 5 minutes later something is happening. No, that's not possible. And also what you see here, the amount of power that is required from the installation is very high. Yeah. What you normally do is you design an installation based on steady state powers. So you would design an installation that can deliver 60 watts per square meter. But if you want to apply or inject water of 30 degrees, you need almost 3 times as much, 150 watts per square meter. Yeah. So that means if you have an installation which can only deliver 60 watts, it will never be able to produce the 30 degrees that you actually require here in this case. So that's also important to take in mind when controlling the building. Some examples on the limited thermal power, a calculation, a taps with a raised floor, a bit like the example we saw before in the building in Paris, a bit the same layout. If I calculate it with the limited surface temperatures for comfort, you get almost 90 watts in heating. Heating, that's okay. Normally, an office building doesn't need so much heating. Cooling can be a problem because you have to limit surface temperatures due to condensation risks, things like that, due to comfort. So that might be a problem. If the building is not really fit, requires a lot of cooling, then you might have a problem there. That it takes a lot of time. The large thermal mass is also important, certainly for control. Let me explain this. So that's the same graph you had before. This is the amount of energy that is used to do that step of water of 30 degrees injecting into the slab. And what's happening here, this line is the amount of energy the water injects into the taps, so into the thermal storage. And this is the amount of energy that's coming out into the zone. Yeah. So you see here, after 12 hours, you see here that you have 0.5 almost kilowatt hours per square meter of heat injected into the zone. But to do that, you needed double the amount of energy to do this. Yeah. So that's very important in using the taps, in controlling the taps with your system, that you have to avoid as much as possible these kind of effects, because to inject half a kilowatt hour into the zone, you needed it's even more, 0.6, 1.2 kilowatt hours. So that's very important to take in mind if you're talking about an installation with taps. Let me show this with an example. This is the office building from Nathan. It's a Dutch company selling, amongst others, Uponor material. What was happening there, they had a tap system. It was really very good design, nice system, heat pump, delivering heating and cooling to the taps, but they didn't have a good control. What was happening, they started heating if the zone temperature was below 21 degrees. They started cooling if the zone temperature was above 22.5 degrees. Yeah. So in a day, I think it was in April somewhere, this is what was happening. So during the night, the heating was on. Yeah. And in the beginning of the day, people come in, put their computer on, the sun starts shining. So the temperature in the zone rises, the heating shuts down, and a few hours later, the cooling starts up. Yeah. So at the end of the day, exactly the same. People go away, the sun doesn't shine anymore. So a few hours after the cooling has shut down, the heating is on again. We tried to analyze the effects on the energy use with a simulation that did more or less the same as what was happening in the building. So we had two cases, the case we measured here, and a case where we did only some cooling during the night. So we prepare the building during the night, we cool it down, and then it's cold enough to last for the whole day. And if we compare the energy used just for the same system, just different control, we see this result. So in the case we measured, for that one day, we had 270 watt hours heating that was required, 430 watt hours cooling. Yeah. In the other case, the other control, we only required 170 watt hours for cooling. So just to show you the impact a bad control can have on the energy use. You have a very good system. A heat pump was running with an SPF of 4 or 4.2 even, so very good. But okay, the heat pump might be good, but if it's delivering heat that it's not really used in a useful way, then it's of course not such a good idea. Yeah, okay, this I'm going to skip. It's going to take a little bit too long to explain. So okay, the control is important. The control of the installation is important. What do I want to do? I have a tap system which is working very slow, but I want to use it as much as possible, because it's supplied, or the heat and cold is supplied by, for example, heat pump system, night cooling system. So installations that don't require so much energy. On the other hand, I always have some kind of ventilation that I can use. It's fast, and I can use it to control the peaks that are inside the building. But how am I going to choose between the two? That's a point where the model-based predictive control is coming in. So what can I do? I can make a control based on rules. Yeah. So just the programmer or the installer is sitting behind the BMS and starts putting in the different rules. If this temperature is measured, then I'm going to take this action. If this is happening, then I'm going to do this. So you have to think about all the different situations that can occur in the system. And it's not always so easy to do. On the other hand, you have model-based predictive control. Let me go to the next slide. What is the difference between the two? So the rule-based control, you have the building, you do some measurements in the building, and based on the values of the measurements, you decide what is happening in the system. Yeah, so that's normal control. The model-based control is working a little bit different. You also have some measurements in the building, giving you the state of the building is at that time. But then the controller has information on how the building and the HVAC model behave. So they have how the building and HVAC system behave. They have a model from the building inside the controller. The controller also knows what is coming up. So he knows what time people are coming in, if the sun is going to shine, what kind of weather it's going to be, things like that. And it also knows how much the energy that the system is going to use costs. Yeah. How much the energy costs, and also how much the comfort is cost. What the cost of the comfort is. That's of course a little bit a difficult thing, because you have to define a balance between, okay, what is 1 kilowatt hour costing and what is 1 degree overheating costing. So that's kind of choice you have to make as a designer of the system to put into the controller. If you look at the rule-based control, we did a lot of variations, analysis of parameters, and actually we came up, the best result is just keep the taps at a constant temperature. Yeah. You can do other things, but it will always be other situations where that measure is not good. So the best thing is just keep it at a constant temperature, at which one, well, we saw approximately 1 degree above the lower comfort limit. Both in heating and in cooling was the same result. So as a guideline, we had that as conclusion, okay, just keep it constant. It's overall, in a whole year, the best solution. What does a model-based predictive controller do? So you have this scheme. This is of course important. You have a kind of knob choosing, am I going to put more weight to the energy cost, or am I going to put more weight to the comfort or the discomfort? That's a bit an option you have as a manager of the building. What is happening then? Okay, this is more control scheme. You have the situation at a certain moment. You have predictions of what is going to happen. You have the model, and you have a kind of set point where you want that you want to reach. Here, this one, and the model in the controller is going to define the input, water temperature, for example, water flow that you have to supply to the building for the next period. Is it working? Well, yeah, it's working. This is a comparison for a heating situation. These graphs are the rule-based control, where we just keep the core temperature, here this one, at more or less a constant level, you see here. What is happening? Well, at certain times, the system heats up the slab. Yeah. It keeps it at the temperature. The ventilation here, the red crosses here, is just at 20 degrees. If we do for the same day the model-based control, you see that something very different behavior is happening. It starts heating at 24 hours, or at midnight, until approximately somewhere in the morning, and ventilation does the same. Does it help for energy? Well, in this case, no, because the controller, the MPC controller, uses 72% more energy than the rule-based controller, but it is able to decrease the discomfort completely. Yeah. Of course, that's the option you have with the turning knob to choose between energy and comfort, of course. A cooling situation, the rule-based control keeps the taps at a constant temperature here, and it's cooling down during the day. Yeah. Now, in this case, the MPC does something which we didn't really expect. What is happening here, it doesn't use the taps, but it only uses the ventilation to cool down the building, in this case. Yeah. Why is this happening? It was a September day. There was sun, so you need some cooling, but the outside air is quite cold. So actually you have free cooling from the outside air. So because the MPC has a model of the building and the HVAC system inside, it knows, okay, now it's not such a good idea to use the taps to cool, because I have free outside cooling from the air, so I can use just the ventilation here to do the cooling. And in this case, of course, you have a serious reduction of the energy use here, 92%, with a certain increase of the discomfort. Again, that's the turning knob you have by choosing between the two. Is it possible to implement this? Yes, we did it in the Geotabs project in a building called Hollands Huis in Belgium. It was a very good building, nicely insulated, 4,000 square meters. It was almost passive house standard for installation, but it was a very heavy building, so large thermal mass. So a very good building. And we implemented the MPC controller there this is for a heating case. What you see here, this was the model-based control for a certain period, where you see here a peak in power, because it starts up in Monday morning. The MPC knows that that peak is not so good, but because it requires a lot of energy, and it starts heating up, and it needs starts heating up earlier, and it needs a lower thermal power to do actually the same job. Could it save some energy? Yes. On average, in the period we had here, it saved for 70% of energy. So just the same system, same building, same use of the building, only a different control. There we had an energy saving of 17%. Is it the way to do in every building? Well, I must say, implementing this required a lot of work, a lot of engineering work. An important thing is to make the model for the controller. The model has to be really good, because otherwise it's going to predict things which are not happening in reality. So it takes a lot of engineering work. The process has to be automized a little bit more, I think. But well, there is a potential anyway. So I think, yeah, that was my conclusion. So the errors are important to take in mind. It has some potential, but it has also some drawbacks. Okay, thank you.